Okay, welcome back. So we are retaking our reading on page 69. Let's get there. And we performed this, we wrote this code. And so we're going to read now on arithmetic compound assignments, assignment operators. Okay, so arithmetic compound assignment operators. Java provides special operators that can be used to combine an arithmetic operation with an assignment. As you probably know, statements like the following are quite common in programming. A equals A plus 4. In Java, you can rewrite this statement. Okay. What just happened? Okay. Excuse me. In Java, you can rewrite the statement as shown here. A plus equals 4. This version uses the compound assignment operator. Both statements perform the same action. They increase the value of A by 4. Here is another example. A equals A modulus 2, which can be expressed as A modulus equals 2. Okay. In this case, the modulus equals operator, compound operator, obtains the remainder of A divided by 2 and puts the result back into A. There are compound assignment operators for all of the arithmetic binary operators. Thus, any statement of the form var equals var expression, okay, can be written as var operator equals expression. The compound assignment operators provide two benefits. First, they save you a bit of time, a bit of typing, because they are shorthand for their equivalent long forms. Second, in some cases, they are more efficient than are their equivalent long forms. For these reasons, you will often see the compound assignment operators using professionally written Java programs. Here is a sample program that shows several OP assignments in action. Alright, so we're going to see code here, and let's take a look. Okay. Demonstrate several assignment operators. Op equals int A equals 1, int B equals 2, int C equals 3. Alright, and here are the compound operators. Okay. Alright, so let's look at the results. A equals 6, B equals 8, and C equals 3. Alright, so let's go ahead and just write this program. We are going to check out the... Oh, by the way, I did some shell integration in iTerms, so the layout's slightly different. I'm listening to music as I speak to you so that I can monitor the audio, how it comes out, because I will say this headset, even though it's an Elite, totally Elite Pro, so it has some issues with the cable, so there you go. Anyway, let's go ahead and get this started. See, session. Okay. Auto composer, okay. Am I in the hash? Okay. So for some reason, after shell integration, I cannot open the composer, and I'm not sure why. And that sucks. So let's just do nano op equals .java. Oh, here we go. Well, I wish I didn't have to do all that, but anyway. Demonstrate several assignment operators. Class op equals public static void main string. Okay. Okay. By the way, if you're interested, I'm listening to Madiel Lara. He's great. I did not mean to do that, but since we're here, okay. Okay. Oh, excuse me. I am so sorry. All right, let's see what's going on here. Okay, public static void main. Okay, so let's see what's happening here. All right, so that's why it's calling it an implicit class. Okay, it's because he thought it was an implicit class. Okay. A6, B8, C3. All right, so we got the correct output. Nice. So let's look again at the book and see if we're right. Yep, there it is. Okay, so now let's look at the increment and decrement operators. Increment and decrement, the plus plus and the minus minus are Java's increment and decrement operators. They were introduced in chapter 2. Here they will be discussed in detail. As you will see, they have some special properties that make them quite interesting. Let's begin by reviewing precisely what the increment and decrement operators do. The increment operator increases its operand by 1. Okay. The decrement operator decreases its operand by 1. Okay. For example, this statement x equals x plus 1 can be rewritten like this by use of the increment operator, x plus plus. Similarly, this statement x equals x minus 1 is equivalent to x minus minus. Alright. So these operators are unique in that they can appear both in postfix form, where they follow the operand as just shown, and prefix form, where they precede the operand. In the foregoing examples, there is no difference between the prefix and the postfix forms. However, when the increment and or decrement operators are part of a larger expression, then a subtle yet powerful difference between these two forms appears. Excuse me. Okay, I think it's because... Okay. Alright. In the prefix form, the operand is incremented or decremented before the value is obtained for use in the expression. In postfix form, the previous value is obtained for use in the expression, and then the operand is modified. Alright. For example, x equals 42 and y equals plus plus x. In this case, y is set to 43, as you would expect, because the increment occurs before x is assigned to y. Thus, the line y equals xx plus x is the equivalent of these two statements. X equals x plus 1, x equals y. However, when written like this, x equals 42, y equals x plus plus. The value of x is obtained before the increment operator is executed, so the value of y is 42, of course. In both cases, x is set to 43. The line x equals x, y equals x plus plus is equivalent of these two statements. Y equals x equals x plus 1. Yeah, I like that. The following program demonstrates the increment operator. Alright, so let's look at another program. Okay, the following program demonstrates the increment operator. Demonstrate plus plus, class increase, decrease. Public static void, okay, in 1, 8 bits, okay. Alright, so let's go ahead and just code it. Okay. Now for some reason here, I cannot open the composer. It looks like I have to first pull up Nano, okay, and then do the composer. I guess that's one of the setbacks of integration, of shell integration. Well, alright. Oh, excuse me. I accidentally opened the program in the background. Alright. Okay, so now that we're here, well, hold on, let me boy. I did not mean to do that. Dang it. All right. So we did it. Okay. We got the right outputs. Let's see if we can make this a little larger. All right. This is good. All right. Okay, so it looks like our output 2341. What did we do? Oh yeah, 2314. Okay. Same thing, except a little out of order, but we got the same results. All right. Okay, so we have about 5 more minutes, and the video will be just about 25 minutes long. So we're just going to read through the bitwise operators and then close the video. We are on page 72. All right, so let's read the bitwise operators. Okay, Java defines several bitwise operators that can be applied to the integer types long, int, short, char, and byte. These operators act upon the individual bits of their operands. They act upon the individual bits of their operands. They are summarized in the following table. You're rarely going to use that. Operator, result, bitwise unary NOT, and bitwise unary AND, bitwise OR, bitwise exclusive OR, shift right 0 fill, shift left, bitwise AND assignment, that's AND assignment, bitwise OR assignment, bitwise exclusive OR assignment, shift right assignment, shift right 0 fill assignment, shift left assignment. Some of these I was not familiar with. Some of them I was familiar with, some of them I was not familiar with. So I, don't use them. Alright, so let's read a little bit, 5 minutes, and then we close. Since the bitwise operators manipulate the bits within an integer, it is important to understand what effects such manipulations may have on the value. So specifically, it is useful to know how Java stores integer values and how it represents negative numbers. So, before we continue, let's briefly review these two topics. Alright? All the integer types are represented by binary numbers of varying bit widths. For example, the byte value of 442 in binary is 00101010. where each position represents a power of 2, starting with 2, 0 at the rightmost bit. The next bit position to the left will be 2, 1, or 2. Continuing toward the left with 2, 2, or 4, then 8, 16, 32, and so on. So 42 has 1 bit set at positions 1, 3, and 5. Okay, so what that means, let me escape this. So it's position 1, 0, right? So this is 1, 2, 3, 4, and 5. So 1, 3, and 5. Okay. Counting from 0 at the right. Thus 42 is the sum of 2 plus 1 plus 2 to the power of 3, 2 to the power of 1, 2 to the power of 3, and 2 to the power of 5, which is 2 plus 8 plus 32. All the integer types except char are signed integers. This means that they can represent negative values as well as positive ones. Java uses an encoding known as 2's complement, which means that negative numbers are represented by inverting, changing ones to zeros, and vice versa. Oh my god. Oh, that is so cool. All of the bits in a value, then adding 1 to the result. Okay. So by inverting all of the bits in a value, then adding 1 to the result. Okay, so for example, negative 42 is represented by inverting all of the bits of 42, or 0, 0, 1, 0, 1, 0, 1, 0, which yields 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay. Then adding 1, which results in 1, 1, 0, 1, 0, 1, okay, and 1, 0. So where did they add the 1? Let's see, 1, 1, 0. Okay, 1, 0, 1, 0, 1. Okay, 1, 0. So it just looked like you flipped the position from the 1 at the end forward. Okay. That's what it looks like. Okay. To decode a negative number, first invert all of the bits, then add 1. For example, negative 42 or 1, 1, 0, 1, 0, 1, 1, 0. Inverted yields 0, 0, 1, 0, 1, 0, 0, 1, or 41. So when you add 1, you get 42. Okay, that's interesting. The reason Java and most other computer languages uses 2 supplement is easy to see when you consider the issue of zero crossing. Assuming a byte value, okay, we got 1 more minute. Assuming a byte value, let me see how much is this reading. Okay. Okay, so it looks like we are actually we'll just read this 2 paragraphs, and that's it, because we are at that limit when the video should be stopped. The reason Java and most other computer languages use two's complement is easy to see when you consider the issue of zero crossing. Assuming a byte value, 0 is represented by 0, 0, 0, 0, 0, 0, 0, 0. In one's complement, simply inverting all of the bits creates 1, 1, 1, 1, 1, 1, 1, which creates negative 0. The trouble is that negative 0 is invalid in integer math. So this problem is solved by using 2's complement to represent negative values. When using 2's complement, 1 is added to the complement producing, okay? This produces a 1 bit too far to the left to fight back into the byte value, to fit back into the byte value, resulting in the desired behavior where negative 0 is the same as 0 and 1, 1, 1, 1, 1 is the encoding for negative 1. Although we used a byte value in the preceding example, the same basic principles apply to all of Java's integer types. Okay, because Java uses 2's complement to store negative numbers, and because all integers are signed values in Java, applying the bitwise operators can easily produce unexpected results. For example, turning on the high order bit will cause the resulting value to be interpreted as a negative number, whether this is what you intended or not. To avoid unpleasant surprises, just remember that the high order bit determines the sign of an integer no matter how that high order bit gets set. Alright. Okay, so he just started using this term high order, and I don't really know what high order is because he didn't mention that right here. Okay, so high order probably means that first one, that first number. Okay, that's probably what it means. I have to play around with that to see it actually at work. Okay, and I don't know why I keep switching to that. I apologize. Putting my hand on the keyboard accidentally. All right, so I think this is good for now. Thank you very much. And we stopped in page 73. All right. Thanks for joining, and stay tuned.